Hey everybody. So here's a little extra video in relation to the composition of functions. This time we're going to look in the other direction, that we've got a function. In this case, I'm calling mine c of x, thinking of it as a composed function. And we have a function here, and instead of composing it with something else, we want to think of it as having been composed of other functions and try to figure out what those functions might be and rewrite this as the composition of functions. And there's not like a set of rules I can give you. We'll necessarily, I think it's easier just kind of seen in practice. But we're going to look for things that can contain other functions. So for example, if I look at this function, I might notice that the denominator of this fraction is itself a function. And so I could think of this function in the following way. If I let f of x be 1 over x, and g of x be the square root of x squared minus 9, then it is the case that if I take f composed with g of x, or f of g of x, what I in fact get is 1 over x squared minus the square root of x squared minus 9. In other words, the function f composed with g of x is equal to the function c of x, right? So I noticed that I'm taking the reciprocal of a function. So if I take that function that's in the denominator and compose it with the reciprocal function, we end up with the function we wanted. One thing to note about this is not unique. There are often multiple ways we could write we call this a decomposition of function, right? We're uncomposing the function. So for example, another way that I could do this function is I could decompose this function is I could think that f of x is 1 over the square root of x, g of x is equal to x squared minus 9, and now if I do f composed with g of x, or f of g of x, I will end up with 1 over the square root. That's the f part, but we're composing it with this x squared minus 9. And again, this shows us that with these choices, f composed with g of x is the function c of x, right? Those are the same function. Okay. And let's do one more example. We could also consider the functions f of x. F of x is equal to 1 over x. G of x is equal to the square root of x, and h of x is equal to x squared minus h of x will just be x squared minus 9, right? And now I'm going to compose 3 functions, right? I'm going to have f composed with, and I'm going to think of it in this order, right? So there's a lot going on here, right? First, I'm taking g composed with h. So let's look at that function. G composed with h of x is g of h of x, or, so looking at my g, we've got a square root function and we're composing it with x squared minus 9. And then we're taking that function that I've explored up there and composing it with f, 1 over f. So once we've composed the g and the h, we're actually back in our first situation. We're composing the reciprocal function with the square root function. Another way to write this is f of g of h of x, right? Or f of g of x squared minus 9, or f of g, the square root of x squared minus 9, or 1 over x squared minus 9. So again, what we've shown is that f composed with g composed with h of x is equal to c of x. Okay, so 3 different ways. You might be able to come up with another way to do this. Right, I can just looking at it, for instance, the argument of the radical here, the x squared minus 9, you could build that out of the function x minus 9 composed with the function x squared. So we could find yet another way to do it. And I wouldn't. There's no particular right way. When we get to places where we're doing this for a reason, for instance, when you get to calculus, taking a complicated function and breaking it down into its less complicated parts can really help us perform some of the jobs that we have in calculus. And so the question there is, what are the nice chunks, right? Sometimes too many functions makes it more complicated, and you might want to break it down as far as, for instance, the example I just gave in words of taking x minus 9 composed with x squared to get that x squared function. That might be a little too far, a little too granular, and somewhere in the middle might be a nice function, a nice decomposition where you've got simple enough parts that the things you have to do with them are easy. But anyways, right now our job is just to be able to do this, and I think it's good to notice when there's more than one option. That's it for decomposition in this video. Just as an aside, it's always a nice practice to look at our function and think about things like domain. So let's just take a quick look at this function x squared minus 9. Right? And depending on how you decompose it, right, the domain comes from one of the different decomposed parts. But just thinking of the function c of x as a whole, let's think about our domain. We know, for instance, that we can only take the square root of positive things. So we need x squared minus 9 to be greater than or equal to 0. Sorry, we can only take the square root of non-negative things, so everything but a negative. But then because it's in the denominator, we also need it to not equal 0. So we're going to take away that or equal to. Right? And now we need to solve this inequality. I like to think of this one graphically. If I imagine the graph of x squared minus 9, oops, it's going to be a parabola like this. And it's fairly straightforward to see where it's going to hit the x-axis. X squared minus 9 is equal to 0 when x equals plus or minus 3. So this is the point negative 3, 0. This is the point 3, 0. So this inequality, x squared minus 9, is equivalent to saying, when is this graph above the x-axis, right? We want the outputs of x squared minus 9 to be positive. That's above the x-axis. So from this graph, that's everywhere but in between negative 3 and 3. And remember, we're not going to be able to include negative 3 and 3 in our domain because that's where it's equal to 0, which gives us a problem with our denominator. So writing that out, that means we can have as our domain negative numbers less than negative 3 or positive numbers greater than 3. And so our domain would be these two sets, these two intervals, excluding this middle between negative 3 and 3. Okay, that is it for this one. I will see you